So let me just take a moment to sort of introduce myself to you, because I think I don't know most of you here. Doug Plata, I am an urgent care physician and got seriously infected with the space bug back in 2012 and have enjoyed every moment of the infection. How about you guys? Do you enjoy it? Yes. Okay. So let me also tell you, I've developed a space advocacy organization called the Space Development Network, sort of a free-to-join organization. What we're looking is for people of very different sort of skills to go ahead and work together and sort of work on individual projects towards a specific plan, a plan for sustainable space development. So if you want to go to developspace.info, it's a rather extensive website, still a work in progress, but very extensive, and you'll sort of see the concepts laid out there. And feel free to join if you'd like to. Okay, so let me just go ahead and give an overview. So I'm going to share with you about how this came about. It was a debate that I was in with Robert Zubrin was on the panel in the debate, and he brought up the issue of greenhouses on Mars being able to have direct sunlight, whereas on the moon it has to be shielded, and so that has some pretty significant implications. And so I'm going to go ahead and sort of broach this issue. It's certainly not my area of expertise. If they taught this in medical school, I think I slept through that class. But I'm going to go ahead and begin to look at some designs and then really identify relevant factors, sort of the key things that determine good choice of design. And then start side-by-side comparing. I'm going to start trying to do apples-to-apples comparison. And then finally, and especially for this conference, begin to look at, okay, what might the ideal Martian greenhouse be? Okay? So first of all, the debate. So it was at this last ISDC, the International Space Development Conference. That's the annual conference of the National Space Society. And there was a panel of 4 of us. And the question is, where first for settlement? I was representing the moon. Obviously, Zubrin's going to represent Mars. Al Globus was representing equatorial Leo, sort of low radiation orbit. And then we had Joel Sercel representing asteroids being the first place for settlement. Actually, he didn't believe that, but they wanted to be comprehensive. So we had those 4 destinations represented. So Dr. Zubrin brought out a point that I really hadn't thought through until this moment, and that is that whereas Mars doesn't have a very thick atmosphere, it does have enough atmosphere to largely or completely block the solar particle events from the sun, coronal mass ejections or solar flares, so that the plants would be able to survive those events. And then he claimed that the GCRs, sort of the constant, sort of high energy but low dose or low frequency of these particles, over time, that the plants, by the time they're planted to when they're bearing fruit, that they're not going to be killed by the GCRs. So if that's the case, then you don't need shielding over the Martian habitats. You can just have a thin, sort of clear wall exposed to sunlight. You don't have to go through the process of using photovoltaic cells to bring the light in. Now, this is something that I hadn't really thought about, hadn't been prepared to respond to it in the debate. And so during the conference, I started speaking with some other people who are, hydroponic sort of people. I did get back with Dr. Zubrin and sort of began putting these ideas together. So this is the idea that something of this nature, where it's fairly, you can get going growing food right away. You just inflate this thing, this habitat, clear wall, and you can start growing the food there if you've got the water and the nutrients. Okay, on the moon, they're not going to. The plants are. My understanding is they're not going to survive a solar particle event, so you got to cover it, which means then you need to somehow get the power inside. So the standard way of thinking about it is photovoltaic cells, and then you wire it into LEDs. Okay, so the downside of sort of the Mars greenhouse would be you don't have to ship the covering, the shielding. You just pile the dirt up. So that's mass that's already there. But you got to go ahead and ship these solar cells, the solar panels, and then there's also the energy conversion loss, right? As you're going from sunlight to to electricity and then to powering the LEDs to produce the light, okay? So I was thinking about it. I asked sort of my hydroponics friend and Zubra, and I specifically spoke with him about the issue of insulation, which is a pretty significant issue. Are you going to be able to, as cold as it gets on Mars at night, how is that going to work? And what I would say is this topic is rather complex. As I got into it, I found it's a very fruitful area to look at. But I think that this is actually a topic that I'm not going to be able to do justice here. I'll begin to address it. But I really think that at some point, at some conference, we actually need to sort of have a roundtable discussion, try to get to the bottom of some of these things. Because if, watching the news from Boca Chica, these issues are going to become real issues, I think, fairly quickly. And I'm looking forward to that. But as I looked into this, I began to realize that there are other factors than just the sunlight. If you're using LEDs instead of direct sunlight, then you can actually start doing some vertical farming. And there's some efficiencies, some mass efficiencies to be found there. Also, in comparing, for settlement, comparing Moon and Mars, the sunlight is, of course, about twice as intense on the Moon than it is Mars. And there's some other factors there as I'll get into. And also, perhaps the biggest single factor, which I will get into in my presentation tomorrow, but that is how fast you can do round trips to the Moon versus Mars. And that has, in terms of the rate at which one ship can do those trips, can make a huge difference in terms of at least how quickly the development of both greenhouses but also settlements would happen. So my presentation here, I'm looking at two basic questions. What is the better location, Moon or Mars, for a greenhouse, and what is the optimal choice for a Martian greenhouse? So let's go ahead and get into that. I'm going to try, it's sort of easy when you're debating to be able to say, well, my idea is better than this straw man idea. We need to make sure that we are comparing the best ideas so that it's a fair comparison, and to try to convert oranges into apples so we can compare apples to apples. So, what are we comparing? The standard way of looking at this issue is, here on the left is the Mars sort of design, pretty straightforward. Do notice that it's a single layer there. Whereas on the Moon, it would be something like this, quite an array of solar panels that you've got to maybe ship there, and then habitats that you've got to cover with enough regolith to protect against the radiation. Okay? But also, as we're comparing the greenhouses, at what stage of development are we comparing? Because especially in terms of ISRU, if you can produce plastics on Mars, which I think we could probably do fairly quickly if you got the power. And then on the Moon, can you extract the metal from the highlands and be able to use that as materials? Then it sort of is an equalizer. So what I'm saying is, because the debate was about settlement, I'm going to presume that the level of ISRU is relatively high because we're into settlement by several years, a number of years, okay? Also, a common straw man argument against the Moon is to say that, well, you have these 14-day nights on the Moon. Okay, not at the poles, so we're going to be starting at the poles. So let's go ahead and compare the poles, particularly these so-called peaks of eternal light that you can get about 90% of the lunar day sunlight. And the poles, you can have 1 million people settle just the polar areas. So I would say let's go ahead and compare poles of the Moon to, of course, the equator of Mars is where everybody says they want to start. Or I suppose SpaceX is looking a little north of there, but not terribly far north. So what are the notional greenhouses? So here's these diagrams. So this is the standard way of thinking about a lunar greenhouse, and that is you've got plants, multiple levels, people inside, also shielded by the regolith, and you got solar arrays on top. Here's the Mars concept. You've got uncovered, but you got some air, so that's protecting it. You got a single layer because of the sunlight, but you don't have people. And I'll explain why you don't have. It's because the people need to be shielded, so there is this issue of how do they work in the greenhouse when they're being exposed to GCRs. I mean, that's what the shielding is for, is primarily protect against GCRs, because that makes up most of the radiation in terms of like millisieverts. So let's go ahead and start to compare the location. Now, these are the notional concepts, and I'm going to get into my recommendations, which are actually different for both the Moon and Mars. So here we go with the poles. The peaks of eternal light would be the location on the Moon, equatorial for Mars. For the volume, and I'm taking a very initial crew of 8 people. For the volume on the Moon would be about 20 by 20 meters by 3 meters. And this is growing space. It's not walk-around space, but growing space for the plants. Whereas in Mars, it's going to need to have a larger footprint because you have only one layer. The typical thing, or at least my design for the Moon, would be a pancake sort of shaped with Kevlar tethers holding the roof flat, so you can push regolith on top. The typical thing for Mars, like we saw in the drawing, would be sort of this Quonset hut sort of style. That's neither here nor there. You can switch one or the other. But in terms of the materials that you use inside and perhaps the structure of the greenhouse, well, this is where Moon and Mars is really fairly different. There is some organics. There's a noticeable amount in the ice, in the L-cross results, that are very useful, especially if you recycle. But you don't want to be producing large amount of plastics from your limited carbon and nitrogen in the ice. Rather, for the Moon, you want to go with metals, which we know there's unoxidized metals in the regolith. On Mars, goodness, you got this wonderful, wonderful atmosphere. And by all means, let's use this along with water. You can produce polyethylene and all sorts of, basically every plastic. For the shielding on the Moon, you got to have regolith shielding. From Mars, in this notional concept, you don't need anything for the plants. Now, for planting and harvesting, on the Moon it's easy. They go into the habitat that's shielded and they can work in there. For Mars, you've got to figure out a way to not have people go into the unshielded area, but you need to go ahead and get the plants to where the people are in their shielded environments, and I'll explain that. And then maintenance of pumps and stuff like that. You also got to figure out how do you do that if the people cannot go into the habitat. So let's go ahead and get into this. Here's Mars. And of course, here's the challenge. People are living in the shielded area, but the plants are growing in the unshielded area. How can you do that? There could be a number of ways. There's this idea that I've heard people say, we'll just have a sort of a sliding regolith shield and some sort of Quonset hut on rails that can sort of slide back and forth. I think it's possible. I'm not really too excited about that because that is a lot of mass. You got to build it up in the first place. It's a lot of mass, and then what happens if it goes off the rails or something like that. Okay. Another way, and I'm not saying this is comprehensive, but another way would be sort of have a track system and then have what do you call these things that? What's that? Well, pulleys, but like they do in the shipping, where it goes along a crane goes along a rail, drops down, picks up the item, picks it up, and then just wheels it right into where the crew is. And now you can go ahead and plant or harvest whatnot, and then you send it back out, and it drops it down the right place. So that is one way of getting around it. Another way, which is a real possibility, and that is just go full robotics, like actually have our artificial intelligence systems going and planting and figuring out where to cut and harvest and these sorts of things. But these things also need to be able to like repair pumps, and that can be complex. I suppose maybe you could pick them out and then bring them in. You could have sort of a hybrid system, bring them into the crew and they could work on it. So there's some possibilities, and I'm not going to jump right now to saying which one I think works best. Now, let me get into some of these, what I call relevant factors, and just comparing side by side. So what about the lighting? So on the Moon, I think if you're going to be going with electrical power, then you jump to the magenta, the red, blue LEDs, and you don't use the energy shining the green light, which is just going to reflect back off the plants. For Mars, of course, for lighting, you use direct sunlight. For the power sources, the standard way of looking at it is ISRU at that stage of development of the settlement and producing photovoltaic cells. Can we produce photovoltaic cells from lunar regolith? The answer is it's practically already been done. Alex Ignatiev, researcher, has taken regolith simulant and has actually produced functioning photovoltaic cells. So I think that technology is pretty advanced. And then for Mars, of course, the power source is the sun. Now, here's where it gets quite interesting. Comparing the two destinations, the sunlight at the peaks of eternal light can get to about 90% of the day is you have sunlight. It really comes in at a sort of perpendicular, well, anyhow, you don't have panels pointing up to the sun because the sun is at the equator, so it's vertical. So if you do 90% of 1,380 watts per meter squared, I left those units out, then you get to about 1,240. Now Mars is in a much worse situation from a power standpoint because it is about just right around 50% of the solar incidence. Plus you're blocking 50% of your hemisphere is covered by the mass of Mars. And then you have these angles in which it's traveling through a lot of atmosphere in the early morning and the late evening. And so I don't know the exact number, but I think it's about 250 watts per meter squared that you can get. When you run those, the comparison there, you can see it's about 20% of the power that you're getting. However, this is sort of made up by the conversion losses of about 15% efficiency on the moon with photovoltaic cells, and then Mars, well, you're getting the direct sunlight. Now, in terms of the plant configuration, I think pretty important. On the moon, if you're doing LEDs, you can have LEDs down the plants. You can have essentially vertical farming. In Mars, if you're using the sunlight, it's 2D. So you're going to have a greater footprint, more mass in your greenhouse. And then the substrate, I think in both places we're going hydroponic. That's what I'm anticipating. Although certain crops, a few crops need soil. Okay, so trying to compare apples to apples, and please don't hold me to these numbers. I'm making a first effort at these. But how much, if we can put a factor, a number of saying how much does it benefit Mars that it doesn't need photovoltaic cells compared with the moon? And I'm going to say it's about 50% of the total mass is represented by the solar panels. But that's just a guess. Now, for the CO2 and nitrogen available in the atmosphere, you've got, in my perspective, if you can be recycling on the moon using the local nitrogen carbon in the ice, then it's the amount of mass of the recycling equipment is probably a relatively small percentage of the overall mass of the greenhouse. Plastics available, I think, is a considerable advantage of Mars. Albeit you can go ahead and extract the metals, but I think producing things from metals on the moon is going to be significantly harder than producing plastics on Mars. No regolith needed. Well, it's a one-time thing that the telerobots put the regolith on the lunar greenhouse. So I think it's a relatively small percentage of the mass. But then the conversion losses are about fivefold. Okay. So on the moon, the advantage of having 3D volume is you're not just growing one crop, but you're really growing as much as like 3 full-size crops. So let's go ahead and give that a 3x factor. The solar intensity is double. Magenta lights, you're eliminating one part of the spectrum, so let's go ahead and give it a third there. And then the daylight, meaning the 50% plus the slight angles at the horizons, let's say 2.25%. Teleoperations, the moon is within teleoperational reach of the Earth. Not so true for Mars. So very arbitrary twofold there. But I think blowing all of this away is the quicker round trips. You can do 79 round trips to the moon with a Starship than you can for Mars. Now, it costs more to do that many trips. But you can grow things on the moon much faster with a set fleet of Starships. Okay, so can we think about some better greenhouses? And I wasn't keeping my eye on the time, so let me go ahead and fly through. I actually think that we shouldn't do photovoltaic cells. I think we should use solar concentrators. These, I believe, could be produced relatively early on both the Moon and Mars, and the efficiency is much higher because you got light pipes going in, or fiber optic cables bringing the light in. So I would actually go ahead and replace it with solar concentrators. And for Mars, I would do the same thing. Thank you. And if we were to do this, now these can be produced locally, so they're not shipped. You don't have that as part of your payload mass, albeit you have the work of producing them, but that could be probably largely automated. In which case, if you can go ahead and start shielding the greenhouses and bringing in light in this manner, and you can bring a lot more light from a larger area in through these light pipes, then you can actually start doing 3D farming on Mars. So here is changing those relevant factors by the different approaches that I'm talking about. So now your volume of growth on Mars is increasing. You do have the regolith shielding. Now the crew can go into the greenhouse and handle things themselves directly. You have the solar concentrators. You don't have the conversion losses like you had in the photovoltaic cells. You still have the problem of the reduced sunlight at Mars, but it's significantly improved by being able to do the 3D, sort of the vertical farming. So my suggestion is Starship, doing a lot of trips to the Moon, but at the same time, starting to do the trips to Mars, and anything we learn on the Moon is immediately applied to Mars. It's not one before the other. It is both at the same time, but using the lessons learned there. So thank you for your attention, and I'm open to questions.
So you mentioned the use of solar concentrators on Mars. So the classic objection to that is that unlike photovoltaics, they're completely incapacitated by a cloudy day or a dust storm, unlike photovoltaics, which still maintain some efficiency in the event of a cloudy sky. Do you anticipate that as being a killer argument for continuing to use solar panels instead of solar concentrators in Martian agriculture?
Thanks, Max. Great question. I did look into that. I looked into the length, the average length of the storms and how frequent the storms were. And the number escapes me, but I think it was about 1% of the time would be blacked out by the storms. Some storms are longer than others.
It's episodic, so while it may average out to 1%, it can definitely last long enough to lose a growth season.
Yeah.
But unlike with solar panels, where you still maintain enough power even during most but all the worst dust storms to perform agriculture.
What I would say is, I think under any circumstance there ought to be enough supplies to bear with if things break down and whatnot. So if there's a storm, you start consuming you harvest early, I suppose, and then you start consuming your dried goods and your canned goods and stuff like that. So it's something that's relevant, but I think it's something that can be planned for. Thanks. I'll repeat the question.
Okay, you could also have a hybrid system where you have the capability of using aerospace for solar cells, in a limited capacity when necessary. I would do that anyway, just to make sure that the amount of sunlight energy is provided to a very consistent level all the time.
So if I understand what you're saying is a hybrid thing where you do have LEDs and some solar panels, or maybe just LEDs in a power system that you're drawing upon? You need power for life support systems, so yeah. So there's.
But the idea is to get you through those times with those dust storms.
Yeah.
And maybe just not enough sun.
Yeah, exactly. Question there? For Mars? For the Moon? Okay, what is your source of carbon on the Moon? Let me absolutely dispel this belief that's out there that there is no carbon or nitrogen on the Moon. Since 2009, the LCROSS results, we know that there's carbon and nitrogen on the Moon. There's nitrogen in the form of ammonia. Okay, that was detected in the LCROSS results, and that's a fingerprint. That's a spectroscopic fingerprint. The carbon is in multiple forms. It's in the form of... so if you're producing propellant levels of if you're harvesting propellant levels of water, then you are producing, you'd have to ask Jeff Greenblatt, because he's done this, he's presented it, he's done it. But if you recycle, there's enough for, he describes as much more than what you need. So it's not a small amount. It's not a small percentage of the ice is organics. Look up the L-Cross results. I encourage everybody to look up the results. Become familiar with them. Okay, I think that's it. Thank you.
Very good.
Art and I were roommates last night. We were joking about being at each other's presentations and heckling each other. So I'm glad you behaved yourself, Art. Was there another question? Yes.
So on the lunar poles, you're going to have the sun kind of perpendicular angle roughly.
Correct.
It's going to be going around 360 degrees. So all those solar panels are collected or photovoltaics are going to have to bring. Have you thought about vertical farming or doing like a silo type of situation? You have all that sideline, so it seems like the moon would be a really good place for vertical farming because you have 90% of the year sideline and it's going around. So you kind of have a cylinder structure for pressure retention, and then you can do some alternating regolith and water kind of exterior to prevent radiation events from fire.
So how would you deal with shielding for those ones?
Exterior, you would have lunar regolith and possibly columns of water, which is, I think, how they're useful. So you could
Absolutely.
do radiation without. And then for the thermally, because that would heat up so much, you could kind of alternate the columns, some solid regolith, some clear, just so that the greenhouse could heat up. Of course, it's acid, really, water bubble.
Yeah. So are you talking about using an outer shell of water to protect for columns? I see. I see what you're saying. Totally new idea. Right. So then the question is enough shielding for crew to work within there? Do you need crew to work within there? So what I'm saying is these are, it's a complex field, and I feel like that the space advocacy community, experts especially, needs to sort of get together and hash through this, and because there's a lot of different good ideas out there for growing food. I love algae. Another question?
Actually, a lot of shielding crew that works in the greenhouse is also on Mars. What prevents them from just wearing spacesuits in the greenhouse?
So there is spacesuits that are like shielding spacesuits, have a lot. Oh, I'm sorry. So as people are working within greenhouse, why can't they just be wearing suits to shield from the radiation? Is that right? Not a bad idea. It's just that you need about the equivalent of 20 centimeters of water to shield against solar particle events. So if you have a smaller shield than that, then when they detect, when they see the solar storm happening and the radiation detectors start going up, you'd need to get out of there into a storm shelter of some nature. So and for the GCRs, a lot of the GCRs are just too high energy. These things are relativistic speeds, and this little thing is just going to punch right through it. So you're still going to get the radiation from the GCRs to a very large extent, like probably about 90% of the millisieverts. Yeah. So polyethylene is really fluorine, yeah. So polyethylene with fluorine that's embedded in it, it's excellent because it has a lot of hydrogen. It has more hydrogen per mass of the molecule than water. So it's even a little bit better than water. But again, if you take a look at the curves, let me show you the curves. Let me just in answer to this gentleman, I've created a little video animation. This is an animation. Let me just scroll through here of a concept that I have for solar drapes, and that is at the poles of the moon. in which you have telescoping towers and you have suspension lines between it, pulling up rolls, drapes. So you have this whole wall of solar power or solar drapes coming up. That would be minimum mass for support structure and maximum power production. So, but back to the radiation. Okay, so there's this graph right here. I wish I could zoom somehow. So this is an important graph for radiation, and what it shows, this is Simonson et al., and what it shows is that as your thickness of shielding increases, the amount of millisieverts of GCR radiation is coming down. It has this sort of curve. And you see the blue is the water. So if you have 20 grams per centimeter, which means, because it's 1 gram per centimeter cube is the density of water, then it turns out that it drops the millisieverts, in this case centisieverts per day, but per year, it drops it to about 50%. So just having your shielding against solar particle events is enough to drop your radiation from GCRs down by 50%. So having that amount of shielding is very helpful. But then you see the regolith, the curve isn't as good, but that means you just need more of it, which means actually for the density, you need about 11 centimeters of regolith to protect yourself from the solar particle events, and that's going to bring you on down. Well, if you get up to 30 centimeters of regolith, that will get you down to about 50%. I'm sorry, what was your question?
The question was about the greenhouse. So we need it here to incident material thing. The question was why can't the crew that works in there basically what shielding is and great part of it was about material actually shielding.
So my guess is PEF is probably a slight bit better than the polyethylene. That's the orange line there. And so to be able to get down to where you're staying within your career limits within a reasonable amount of time, especially if we're looking at settlement, then the amount of polyethylene fluoride shielding that you're going to need is going to be pretty substantial. It's doable. But frankly, regolith, just push more of it on. Well, let's talk later, yeah. Yes, well, you barely got it first.
For the workers that are going into the Mars greenhouse, if they go out there at night only to do the work, maintenance and stuff like that, then they don't have any radiation.
They don't have any solar radiation, that is true. Galactocosmic radiation comes from it's anisotropic, it's from every direction. And that makes up, I think it's about 90% of the total radiation dose attributed towards cancer. Yeah. You're right. There was a question back here.
When you're thinking about a greenhouse, actually what's the actual area or acres you're talking about? And versus how many, versus the big how big area?
Yeah. My best understanding is that, okay, so in terms of like the living area, what percentage of the area needs to be growing food? Okay. I believe that it is about 30 to 35% of the volume needs to be dedicated to this very intensive hydroponic growth system. And hydroponics, I mean, it's a pretty advanced level now thanks to the cannabis industry. And you can get per cubic volume, you can get much higher production rates than fields. Yeah. So I'm gonna take the liberty for if any of you want to leave. I mean, we're done, but I'd just like to show you the Space Development Network website. So just a little self-promotion here. This is a website that is nearing completion, and it shows different aspects leading to settlement. So there's one, the plan for sustainable space development, which gets into how the infrastructure can be established. And at the next level, you can drop down, like here, you can go to the radiation page. So it's a sort of an easy structure. Here's the crew and their health. So this gets into initial crew, which I think if we do it right could be extremely historic, whether on the moon or Mars. If we do it right, these people could go down to history similar to like Plymouth Rock or God forbid, Christopher Columbus, but the positive part of Christopher Columbus. Social status is fascinating. If you have people away from their family for more than 18 months, according to military standards, then they typically ship the family and establish families there. Okay, how are we going to deal with that when we're doing, 2.6 or 2.5 year missions to Mars or more than 18-month missions to the moon? I advocate that we actually start thinking about sending families. If we're going to be having them there that long, but the families cannot include young children because of the hypogravity issues. And then some animals, a lot of fun there. And then just the reality TV, not reality TV, but television series, virtual reality, et cetera. So the inspiration, dancing in 3/8 or 1/6 gravity is going to be a new thing. I'm actually meeting with faculty, dance faculty, they're excited about this, at the University of Arizona at Tucson. Just think about the physics of dance. When what could you do in one leap? It'd be more like high diving in terms of the number of things you could do while you're up there. Artificial gravity, the psychology is interesting, and dust mitigation. And then the international, now I'm oriented towards the moon, and so this is what are all the things that could be done in terms of a very large international lunar exploration phase. And I think this is the intermediate step. I think when we talk about funding, steps towards settlement, I think if we can get it low enough, and I think the Starship is going to definitely be low enough, practically all countries, about 2/3 of countries, could afford to purchase a seat for exploration. And I think they've got far deeper pockets than any one individual citizen in their country. And so I think this intermediate phase of international exploration is going to be the transition, way to increase flight rates, get price down to where private individuals can go. Achieving Earth independence is a project that some of us are working on, being able to say, when we get to where there are physical resources on the moon and on Mars, how can we use those to be able to reduce the amount of mass that's shipped? So you get to where you're shipping people and electronics mostly, and for Mars, there are provisions on the trip. And we're making progress to the point we are actually beginning to demonstrate these things. And it's a very exciting project. If any of you could contribute some aspect of that, that would be appreciated. Space policy issues. And then also, I would like to see an analog base, a Moon-Mars analog base that would be more development-oriented rather than exploration-oriented. So, love to talk with any of you if you would like to talk about these things. All right, thank you. Thanks for that.
Yeah, you got it. It's not very long. Okay. Yeah, you took it earlier. Okay, thank you so much, Doug. That was excellent. Again, one last try. Is Saranjana Trivedi here? No. Okay. So what that means is you've got about 20 minutes to have a break. And we'll reconvene here at 5 o'clock on the dot. And hopefully our next two speakers will be here.